we'll talk about, instead of just general JPEG access, we're going to talk a little bit more about how it's being used in media live production, and trying to be a little controversial here, sharing practical experiences beyond greenwashing. Make sure we're not just talking a good game, that we're actually trying to do and help improve the world a little bit here. So probably should level set first. What is greenwashing? It's when a company or an organization, they want to exaggerate or falsely claim to be environmentally friendly to improve public image while continuing to practice practices that actually harm the environment. So it can be misleading advertising, vague or unverified sustainability claims, or superficial environmental initiatives that really don't lead to any real change. So the goal is often to attract your eco-conscious consumers without making any really meaningful efforts to reduce the environmental impact. So sustainability goals, where are these coming from? The United Nations has defined sustainable development goals, really emphasizing reducing environmental impact. And so really those focus areas are on carbon footprint, energy efficiency, waste reduction, and sustainable resources. So in the media industry's role is really about how are we adopting these green practices, reducing these emissions, and promoting that awareness. And as you can see, many of these new practices can also involve, cost reductions. They don't have to be more expensive. You don't have to add a lot of cost by becoming environmentally conscious. So green practices don't necessarily have to mean more expensive. So where are we at today? I mean, just sort of taking a high-level view of what we've done so far in the media industry. In reducing our carbon footprint, we're focusing more on using renewable energy, putting in LED lighting, energy-efficient equipment to help reduce the amount of power we're using in media. In remote production, we've reduced them down to travel needs, reducing emissions. Sustainable set design, reusing materials, minimizing waste, leveraging, we got all these new virtual LED walls, so you don't have to keep tearing up and tearing down sets, and you can reuse these systems over and over again. And as far as eco-friendly broadcasting, such as more and more towards cloud-based workflows, it helps centralize tools and resources, to help cut that energy consumption from multiple sites to a centralized, and with dedicated equipment at each, without having to put dedicated equipment at each site. This flexibility is really helping support multiple different workflows out of one site rather than having to have dedicated sites. Of course, got to have the overall JPEG XS summary of how we're increasing efficiency, sustainability, and with this lower power. The goal when we created the codec was to create the most advanced, standardized, lightweight codec, and really the goal was to replace uncompressed video. So it needed to be visually lossless. You had to have very high constant quality, but to make it more sustainable, it needed to be lower power, lower complexity, high speed. To make it fit into the new cloud-based and software-based kind of world, it needed to be very highly parallelizable. And so part of that was also making it very platform agnostic. So anywhere from ASIC to FPGA to CPUs or GPUs, it can run on any one of these platforms. And of course, to make it as close to uncompressed as possible and meet very low latency or no latency. So we're down in the microseconds, for that down to 16 lines of latency. And one of the nice functions of wavelet scalability is really no matter what resolution you want to throw at it, it can be easily adapted with JPEG XS. And of course, finally, it needed to be a standard. So it was standardized to the JPEG committee and then became a full ISO standard. So when you look at the enhancements that with really, what does, trying to put a little rubber to the road here of what does JPEG XS help increase that efficiency? First, it was the first ISO compression standard that really was designed with sustainability in mind. So it's very low complexity, low power, and with very minimal processing requirements was the primary values to create the codec. And as part of that energy efficient processing and transmission, it uses less computing, so you're lowering the power, and you need a lot less memory, thus reducing your carbon footprint further for the encode and decode process. Of course, with any codec, you're reducing the amount of bandwidth needed, which also reduces the amount of energy you need to transmit it and transport it. And then with some more recent innovations, we're starting bringing out more proxy capabilities into the codec as well, so now you can do a lot of your transmission at even lower bandwidths down at 1K, and then when you finally want the 4K, you can switch and it'll now give you the 4K stream, so you can save more efficiencies there. And then of course we've got all these remote and cloud-based workflows really helping support this sustainable media, making it more efficient and flexible, and using that hardware across supporting multiple sites rather than having to have multiple sites with multiple different pieces of hardware and a much lower bandwidth. So what we're going to do here is through the rest of this presentation, we're going to talk about how each of these examples we've come up with align with the 3 R's: to reduce, reuse, and recycle. Reduce, an example, less bandwidth and make it more less energy required. Reuse, extend the life of existing infrastructure with the flexibility to enhance the capabilities. And we'll show an example of J2K moving to JPEG XS. And then recycle, support greener broadcasting workflows with, trying to minimize that waste, getting longer life cycles so you don't have to replace the hardware as often, and so you can just start through enhancing your existing hardware and software solutions. So we've done a lot of talking now at this point. Let's see if we can point to some real-world examples of where we've actually accomplished some of these goals. And really highlighting, we'll go through each one of these and highlight how we've been able to reduce, reuse, and recycle in each of these examples. First one, we'll point to our friends at the IABM. In 2024, the China Media Group did a full remote broadcast on this new archaeological discoveries in Wuwangdun. And they were leveraging a Grass Valley LDX 150 camera that had JPEG XS coming right off the back of the camera. And we're able to basically do a full JPEG XS with SD-WAN broadcast in China. So how did they reduce? By enabling a more efficient remote production, so a really nice remote production example. Minimize the need for extensive on-site equipment, less personnel, and all the associated carbon emissions that come with that. Reuse, they ran over the existing public network, so they didn't have to put in a new network, anything, they used what was already there. And recycle, the primary focus was really on reducing and reusing resources. So maybe the recycle was not quite as obvious here, but recycling of existing workflows was an example. You didn't have to go create a new workflow to do this. You just did it remotely. And then our second example, and we're probably seeing this all over the place as well, is the centralized video assistant referee systems. So slow-mo TV, using JPEG XS, and the video assistant referee system. So basically whenever there's you need that video assistant referee to make a decision, they take that back to a centralized center and where those decisions are made, and then they make those real-time decisions in the games. Talking to Andrew from Evertz, essentially the same thing's happening with the NFL, where they take all the referee challenges back to New York to decide which is was the correct call made or not. And so they centralized all that capability there too. So reducing, once again, centralizing those VAR operations. You don't need to have multiple on-site setups, so this is cutting down on the amount of equipment you need. Reuse existing network infrastructures, you didn't have to put in new networks for that, and maximizing the use of current resources. And then recycling repurposes of traditional broadcasting workflows, just integrating more modern technology to enhance the efficiency and sustainability. Our third example comes from MediaLinks with the nationwide media network upgrade they did. They really moved everything from JPEG 2000 to JPEG XS for their contribution applications. So they have this countrywide network transmitting the JPEG XS using their existing media gateways equipment, which allowed for this painless upgrade and really an enhanced performance and lower power, which by lowering power and all that, you're increasing your reliability. They switched over close to 1,000 pieces of equipment, chassis, on these with several thousand services running on it. And so where did they reduce? The power consumption, here's one of our first ones that has some real tangible measurements on it, where it was a reduction of 20 watts per 4-port video card across thousands of cards, so we can do the math and add that up. And they also get one of the other advantages moving from JPEG 2000 to JPEG XS, they were able to see the latency virtually become undetectable. It's one of the advantages of moving to JPEG XS. and giving you really much more of an uncompressed video feel than they had with JPEG 2000, which is a frame-based kind of codec. And then reuse, they take their existing infrastructure, they upgraded it without any major overhauls, and they actually got an increase in capability as well. They had 2 times the number of ports on each box now. And then how'd they do this? Of course, it was, in this case, it was based on FPGAs. They were able to just reflash, update the new firmware on the boxes, and got the additional capability out of those boxes. So looking a little deeper into the, some of the ripple effects of this extended life cycle, as I'm alluding to here, you can get up to a 10x power reduction by moving to JPEG XS High or JPEG XS TDC. With its low latency and the bandwidth efficiency, you get just a more robust remote production capability. You need fewer people are needed to travel, so you're lowering your overall cost and associated CO2 travel-related emissions. We have one U.S. broadcaster cited a recent major global sporting event, and they basically were able to reduce the amount of people they needed by 10%, which translated to almost 150 people that didn't have to travel to the site. So you get up to a 10x power reduction compared to current JPEG 2000 implementations, which now the power gets low enough you can actually do power over Ethernet and get into much more lower power designs. From a actual logic element, how did they get the 2x more codecs into the same box? I mean, you're using 3 to 4 times less logic elements for JPEG XS versus JPEG 2000. And then the other nice benefit came out of JPEG XS is you no longer needed external DRAM. So it actually dramatically simplified the designs by just running it on the SRAM inside the FPGA. With TDC, you do need a little light DDR in there, but it's still just a one compressed frame. It's not even a full frame that you have to store there. And so you can sort of see the comparisons of the bandwidth in the bottom right of, well, obviously with high, there's none, but less than 20 gigabits per second bandwidth needed versus we were over 60 to 68 gigabits per second that was needed for JPEG 2000 on that DDR bandwidth. And then our fourth example comes out of Japan with our system integrator friend there, Village Island in Japan. Where the goal was to upgrade to 4K 8K video. Requires significant bandwidth, which if you just did it the way we used to do it, it'd need new cabling infrastructure, new switches. And so they went about it by trying to leverage what was already out there, the billions of meters of Cat5 cable that's out there. And JPEG XS enabled this 4K or 8K workflows and kept it on a 1 gig/10 gig networks that were already there and on existing Cat5e and Cat6 networks. So they were able to reduce through preserving their reasonable, keeping it at a reasonable bandwidth and not necessarily have to go to new networks, new fiber, new switches, and keeping very low latency, 4K 0 latency, and visually lossless. And they were able to keep that on a 1 gigabit Ethernet network. And if you're on 8K, they were able to keep that down to onto a 2.5 gigabit Ethernet network. As far as reuse goes, obviously, very good example of how you're reusing your existing materials here and reducing your electronic and building waste. And then on the recycling side, they just keep using the legacy infrastructure. You're not creating any recycling. You're being able to keep utilizing the existing equipment. And then our final example here actually comes from when we took a much smaller snippet of what Thomas showed yesterday on the big NHL one, but showing the JPEG XS capability up in the corner there of his NHL example yesterday with cloud-based broadcasting using JPEG XS for that efficient 4K video transport. And so once again, reducing the amount of on-site equipment needed and the associated energy consumption that goes with that. They did this in collaboration with a peer TV and the AWS Elemental Media Connect, enabling this low latency, visually lossless video contribution to the cloud. And so in this case, a live sports production, would take at least usually one production truck and at least 20 people to manage that. So here's another, a more hard metric we found that, one of those trucks can generate an estimated 2 metric tons of carbon to have to run it there at the facility. So, and that leverages times the number of trucks you'd have to roll up to each of those facilities. So the environmental impact compounds with each truck, and as well as if you're an international exhibition. So that's getting at least a little bit more towards some more measurable numbers as well. I think that's sort of the goal moving forward, is how do we put more and more measurements on this. So we're minimizing the energy consumption through that software. So this is really more of a software implementation flow of the encoding and decoding, and reduces the need for that high bandwidth infrastructure, also leading to lower carbon emissions. And we're able to reuse, the existing cloud infrastructure. I think this is, cloud infrastructure is always evolving, but you're able to leverage what's out there today, and using the existing workflows. And then on recycling, you don't need all that on-site equipment, promoting the reuse of that cloud-based resource and reducing that e-waste. So then taking a look at it, as we talked about, it's really platform agnostic. You can go from hardware. We've talked a lot about how the FPGAs can be upgraded, but it's also very software flexible as well. And so JPEG access on you can really get single core performance. So it's really quite hyper efficient in software and cloud-based applications. Current implementations for an HD video stream at 60 frames per second can run on a single CPU core. So, so it makes it quite appealing for these low latency applications in a software environment, really when you need the fast processing time and low CPU consumption. And on top of that, it gets even better if you do wavelet proxy, where you're doing 1K instead of 4K. It's even easier to do on software. And then I was trying to do a comparison here against some of the software-based 264, 265, x265 in the cloud, and how many cores it takes to do that. And as soon as I throw up one set of numbers, I said, okay, you really got to put the whole matrix up here, because this can become a very big debate of how many cores does it take, what's the optimal performance. But you can see anywhere from, if you're doing very fast or ultra fast, it can be not too many cores, but if you get down towards slow and very slow, it can end up being quite a lot of cores to get that kind of quality out of H.265 or 264 in the cloud on software. So in conclusion, I'm stating no greenwashing. We actually got live examples here where we're actually helping the environment. We're moving in the right direction. So I think we would argue that JPEG access has already helped lead to significant improvements in bandwidth efficiency, power reduction, and environmental sustainability as we make further improvements in the media production flows. Caveat here is, don't have as many numbers as we'd like to have here, and that's sort of our goal. Actually, is to keep working on this for the next couple years. We're hoping to just keep enhancing this presentation, putting more and more meat on the bone. And we don't have precise carbon footprint figures, but I don't know if you guys know this, but I know even in Europe right now, they have to report every employee's carbon footprint at the end of the year in Europe, at least in Belgium. They have to make that report back to the government. What was your environmental impact each year? So there's a lot of activities to actually start putting more and more measurements on this stuff. So that's sort of our goal, is to start putting more and more measurements on this in the future. So energy efficiency, we're reducing power consumption with the low latency and low complexity compression. We're optimizing the resources through enabling the reuse and upgrading of existing infrastructure and extending its life, as well as lowering the transmission bandwidth needed. And then real world impact, that was tried to show here with these examples, with remote production in China, real-time use in live sports, and 8K examples in Japan. And then sustainable practices, see long-term benefits will be with the reduced bandwidth requirements, lower power, and minimal waste. And somebody else made a good point, or mentioned to me, so we're not just seeing this in the broadcast industry as well, we're seeing this across other other innovations across other markets, like automotive is starting to pull JPEG access kind of compression, more raw compression on that side of things, but into the automotive space. We're seeing that in medical, as well as machine vision for JPEG access as well. So it's not just our industry that's being able to take advantage of this. So thank you. And like I said, on the bottom right there, please reach out to us. We really want to keep developing and enhancing this, and obviously we're willing to share it with anybody else, but we want to start being able to show more and more metrics of how we're making these improvements in the industry. So if you've got other examples we should be talking about, please reach out to us and let us know. Thank you.
Thank you, Ben. Any comments or questions? No? All right. thanks very much. All right, John. John is here to talk about something we were talking about last night, activity within the VSF that seems to have reawoken and has a lot of interest, so take it away.
Good morning. I'm John Dale with Media Links, for those that don't know me. And a couple years ago, we finished VSF technical recommendations TR07 and 08. And in the past couple months, there's been a number of requests for some updates to those documents. So we've just recently reformed a team to go over those requests. We've only had one meeting since this came up, but I just wanted to provide a little details on what we're seeing and how that's progressing. And then also, if there's any folks that want to join the team or provide some input, you can reach out to me. So we'll take a walk through this. There's 34 VSF members that have joined the activity group. We've had one meeting. There was 21 members attending that meeting. So this does seem to have some significant attention. The goals for the activity group pretty much have been sorted into two categories. One is to add JPEG XS temporal differential coding capability sets or profiles to the current work for both TR07 and TR08. And then the second piece is maybe kind of a catch-all, but essentially to provide clarifications in the documents for better understanding and more consistent implementations. And I will mention this as just sort of a topic. JPEG XS can be implemented over various hardware and software platforms. And in the past, if we talk about JPEG 2000, it was mostly implemented in hardware. And the hardware implementations tend to be fairly consistent and uniform. The software implementations are a little bit different, and I think the second point there is that there is some difference in understanding of the standard and implementations between the two, and they don't always play well together. So that's something that we want to try to address as we move forward. So first piece of this, we just talk about the temporal differential coding. So the main point here is that we want to add capability sets for temporal differential coding. Just wanted to explain briefly a little bit about TDC. This makes use of a new coding tool that allows the wavelet coefficients to be predicted from a frame buffer. The frame buffer is compressed memory buffer that always keeps track of the last version of the wavelet coefficients. So it's continuously updated with each new frame. So obviously you're going to use more memory when you do this, but it is a mechanism that can optimize quality at a given rate or allow reduced bit rates. So it's an improvement in JPEG XS. There's a number of different ways or settings for this, so that the user would have some capability of setting that. You see that in the next to the bottom bullet there, that there's different levels for 3 bits per pixel, 4.5, and 12 bits. The higher compression needs more memory. So that's new items in JPEG XS. Of course, there's no profiles in TR07 or 08 for this yet. So that's one of the things that has to be done. We look at this. In section 10 of TR08, there's capability sets and interoperability points. So one suggestion is to add TDC capability to this section of the document. The TDC set could be a single table. However, in the existing table, it's divided by synchronous, asynchronous, IPMX, full HD, 4K, and 8K capabilities. So we might have to break it down in the same fashion. We'll have to determine that so that you could have a separate TDC capability set that's broken down into multiple subsets. So that's one way of doing that. We'll go over that and figure out the best way to do it. And then the last item on the bullet list is that for Tier 08, we refer to RFC 9134, which describes the RTP packet and packet structure for JPEG XS. There is a slight change that's needed to that document, so the team will liaise with the folks that are working on that in the IETF and make sure that that document is revised as well. So that was the first category on TDC. The second piece of it is just overall document improvements, and this is specific clarifications to allow more consistent understanding and implementations with better interoperability. So there's a wide range of topics that have been brought up already. I think there was about 20 different items on the list, and we're still collecting items for this. But I just figured I'd mention a few of the topics that have come up. This was a couple years ago when we finished TR07. We had found one or two errors in H222, and the ITU group agreed to make those corrections, and they have actually been made since then. But there is a little bit of confusion there. If someone implemented and didn't understand what we had said in TR07 and used the original H222 documents, they could have done some or made different implementation, especially relative to interlace handling. So that's something we want to be more clear on in the TR07 document. Perhaps adding some examples of how to do that so it's really clear. And then this is kind of a big point that we've seen, that in terms of the elementary stream buffer and signal handling, the JPEG XS is such a minimal latency codec that even a couple milliseconds of jitter, de-jittering that, doubles or even triples the overall latency of the base product. So you have to be really careful about that. Like 2110, where when that standard was done, the timing and buffer models were considered, and you wind up with narrow linear or wide profiles. We may have to do something like that for JPEG XS in MPEG-2TS, which is kind of a new approach. But we may have to mention or add some type of information about that in the standard. Last item is just an example of this. There's a field that is defined differently in TR07 and TR08, and that's fairly inconsistent. So we'd like to correct that in the next revision. So this is just sort of a few of the examples of requests that have come in, and we're still collecting requests before we actually dive into each one and figure out how to revise the document for them. So just an overview on our schedule. The activity group is going to meet every 2 weeks. We're right now trying to capture specific goals. Then we'll review those and clarify them and determine and agree on the document changes, and then publish revised new documents. We haven't estimated the time of the effort because we haven't collected all of the individual information, but I could probably just, roughly guess, probably 4 to 6 months to complete all the work. So that we'd have, I feel fairly confident we should have a new updated versions by the end of the year. That's just a kind of a swag at that right now. And thank you for